They don't get anything about like how to watch your life. We first found this we watch workshops because it tells you the same thing or I have workshops. So I don't watch it. Mention the workshops specifically. For 10 minutes, but then this is the other side. You need to minutes for the workshop. And that might take 30 minutes. Or in a team, yeah. Especially for the rangers, that's a good way to get into it. We got your goals at 5 minutes. Yeah. talk really loud, I think my computer on the left. Okay, so actually, and then one counts as that. So actually, just 0 and 1. Honestly, that is better. Yeah. It should. Does it automatically? Yeah, that automatically records. If the light is less than 12 hours.
Sure, you that's much here.
Yeah, so our reasoning behind that was since we're have to do motors. That way we're like some limits of motors. But the different motors are actually the ones that instead of just having our motors floating doing actually nothing technically happening. We're like making trying to make sure there's 0 liters. So they have to use our motors on the ground. Basically, just like if you use any motors. That's it. Pause on. So it's gonna start. That's what Welcome everyone. Thank you for coming. So we're gonna start the info session. Yeah, woo!
I'm a Mac student, I don't know computers.
Yeah, okay. So we'll start off with introductions. My name's Ethan. I'm a VP Comps, part of IEEE Concordia. IEEE is the Institute of Electronics and Electrical Engineering. We do a lot of different things. So we have a couple projects. We're working on a robotic arm. Coming up, we're working on an e-bike. And then if you guys have ever seen like that Boston Dynamics robot dog, we're gonna be working on stuff like that. So we do big projects like that. We do workshops similar to this, usually once a month. Last month we had an intro to C++. Before that, an intro to microcontrollers. And then we have lots of competitions, and that's what I'm in charge for. So this is one of them. Later this year, or next year, our big one is RoboWars. It's SumoBot competition. Winners can go compete in Japan. It's pretty cool. But yeah, that's me.
So I'm Maria, and I'm a co-VP Competitions for Women in Engineering. I'm so excited to be promoting this event, to promote women in such an event with the IEEE. So I'm so excited to have you all here.
And I'm also co-VP competitions at WIEEE alongside Maria.
Actually, wait, leave it on this. Go back to that slide real quick. All right. So what is Formula WIEEE? It's what you guys are here for. So it's a very kind of like beginner-friendly robotics competition. So what you guys will be getting are these. So essentially, you're going to be making two-wheeled robotic cars with basic supplies, like you got your microcontroller ESP. All these details we're going to go into later today. And with these, you will make a fully functioning car that you can control from your phone. And on the competition day, you guys will be racing, kind of like F1 style, or Mario Kart if you prefer that. But yeah, it's a good learning experience. You'll learn all the basics. A lot of this stuff you probably won't touch until later years. So it's really nice, from my personal experience, to get started earlier, because this is the actual fun stuff. And so yeah, just some details. On the competition day, there's a couple different categories we'll get into later. But again, you're gonna be building these teams of 3 to 4. And everyone kind of has the same parts and base for code. So the way to win is innovating. You can follow the tutorial on the very basics and have a perfectly working car, but most other teams will probably have the same one. So the way to win, you're going to figure out how you can optimize code, how you can optimize your chassis, because that's what we're not supplying. So you can do 3D printing, you can do a foam board, you can do cardboard. So you can prioritize weight, you can prioritize protection. Since you're racing with other cars, you might bump into each other. So there's a lot of things to consider that might give you an upper hand in the races compared to everyone else.
So just in terms of some of the constraints for vehicles and also in terms of the track, so it does have to meet the size and safety regulations. So your robotic car has to be 7 by 10. It cannot exceed that size. Also, in addition, it has to be, like the motor has to be contacting the ground at all times. And for the track, we're not going to be giving you an idea of what the track is going to look like. You're going to have to find out what that is on the day of the competition. But you are going to expect speed zones, maybe sharp turns, other obstacles, maybe different terrains, but it will be like a smooth surface. And we are going to provide you a rules and guidelines documentation later on today for you to get a better understanding of all the rules that you need to be aware of. Okay, so for the event format, so we're going to have a sprint phase and qualifying round together. This is going to be done individually with your own cars alone. This is mainly for inspection and to check that your cars are safe to race with other cars. It's also like to check your sprint, if you're qualified to race. And after that, like the top teams are going to go to the Grand Prix, and this is where the actual race begins. So this is basically the timeline, how it's going to go. At first, we're going to inspect your cars. We're going to make sure it meets the regulations, the tutorials we guys sent you. And then we're going to have the races, the finals, and after that, there's going to be awards. So, yeah.
Real quick to add on, again, some of the reason why we're going with this format, I'm sure there's a couple of you here who like watching F1. When we mentioned qualifying, that's what's going to determine your order when you're doing races. Because qualifying, you're driving solo, but in the actual races, it's 6 cars at once. So that order is going to be determined by your qualifying lap time, but also you're going to be crashing into each other. That's going to change things. That's the fun part too. So.
Also for qualifying and everything else, your penalties count as part of the scoring. So please read carefully the PDF we're going to send you on penalties, not to purposely crash other cars. It's very important for scoring and for qualifying. So, yeah.
Oh yeah, so prizes, big incentive. There's 4 different ways to win. Prizes, if you guys are wondering, we're planning on getting those like $20 to $30 Lego F1 sets. I think that's pretty fun. But so there's 4 ways to win. You could win the Grand Prix, which is the main event of the race. The sprint winner, which is going to be just a 5-meter straightaway. You guys will have 2 tries, get your fastest time in those 5 meters. So based off this, you can always prioritize one competition or the other. Like if you want to just get the fastest straightaway time, you could do that. Then maybe you do terrible in the Grand Prix, but at least you did good in one of them. Or you could do for both. So it's kind of the options are there for you. And then the last 2 options is just the IEEE pick and then the Women in Engineering pick. We're just going to pick our favorite team, not necessarily based off of performance, but maybe based off of like, do you guys have a cool theme? Do you guys all show up in like some outfit that's your team? I don't know. Just, you can have fun with it. And we're picking based off of that.
And so for part of that, we want your car to basically have like a way of identifying like who your team is. So you guys must have your car numbers on your vehicles. And it is also up to you if you want to design how your car looks like, maybe make it look more formula themed, that's up to you. But just make sure that you do have the number on your cars.
And that will be like, that's part of like the IEEE and Women Engineering pick. Like if your car's cool and maybe it doesn't perform the best, I mean, that you can still win if we think it's cool, so.
So thank you so much for being here and for everyone online. We're so excited and we're going to post a lot of updates on our Women Engineering Instagram, so please follow us. And yeah.
So now what's happening? We have a workshop starting closer to 2. That's going to go super in-depth about everything. This is what we'll be posting the slides as well that you could use to build your car throughout these next couple of weeks. But one of our members from IEEE, he was last year's VP projects. He's done crazy projects, but he'll be teaching it. So right now we can, if you guys, I guess we can start lining up, but we're going to start assembling your teams because we have the teams assembled and we'll start giving out kits because the workshop, we're going to do it live and you'll be able to, you know, set up your microcontroller on your computer if you have not done that before. And we're just going to help you out with the basics.
And if anyone wants to change their team, like right now, if you guys met each other or something, please come up now so we can change them before it's too late.
Actually, yeah, let's do that now. So anyone who like wants certain people on their team, you can come up now. Yeah, also questions.
No one has questions?
If we're missing teammates, so maybe like.
We set up teams for you guys, so if you want to change or you met someone right now, you can just let me know. Other than that, guys are going to send you the teams that we chose.
7 by 10 what?
Sorry?
7 by 10 what?
Inches. Yeah. We have teams for everyone. So if you you don't know anyone, we've assembled teams for everyone. Yeah. So no one's solo. Yeah. So this is going to be posted online. It's a recording as well. So you can come back and watch the recording anytime. But yeah.
And the code and everything.
I would
Guys, if I can have your attention, last call if anybody has not picked their kids up. Show of hands, everybody has their kids? Alright, kind of,
Yeah, go ahead, go ahead.
Alright guys, we're gonna start the workshop. I have a question to ask you. So, unfortunately, the light control in this room is not working. So, lights on or lights off? Off. Off? Everybody's good? If you have your laptops, you need to take them out right now. This is gonna be an interactive workshop. You're gonna work on your laptop, so there won't be an issue of no light. And you're not gonna be working with any electronics right now, so you don't need to worry about it. The only thing you need to worry about is plugging your ESP, your computer into your laptop, which you should be able to do it now. All right. All right. So this is going to be close to 2 hours of workshop. In this workshop, this is the workshop for basically intro robotics. The challenge you're going to be facing is purely a robotics problem. You need to make a RC car using electronics, control them using wireless means, control them using your smartphone. There are multiple ways to do it. We'll talk about all of that. And then, so remote control, you need to do electronics, you need to do programming, which is the amalgamation of robotics. You need to have electronics, programming, and mechanical design. You need to make the RC car on your own too. So essentially what we're doing here is robotics. Let's just dive straight into the presentation. Before I start the workshop, a little bit about myself. I am a 4th-year computer engineering student. Throughout my co-ed time, I've been participating in a lot of robotics-related, electronics, programming-related competitions, projects, other stuff, especially through my collaboration, my participation in IEEE Concordia Club. Last year, I was part of the projects team, and because of that, I was able to partake and create many of my own projects. And so, basically, a lot. And to say this in a short time, I started with knowing nothing. My first programming was Cohen 243, or Intro to Programming class for all of you, where you learn C++. That was my first introduction to programming, and we have tried very hard to keep this competition very beginner friendly. You're going to learn a lot of higher level concepts. They are all boiled down to their simplest methodologies, so you can implement them, and you don't really have to go really into deep about how things work. Because it's an introduction, it's not an engineering course. Right, so if you choose to pursue this path of electronics, robotics, programming, your future holds a lot of cool projects. You can bring something to life that is in your brain. You can bring an idea to life. That's the whole point of you becoming an engineer. So today's goal. What are we doing in this whole workshop, and what's the point? The point is, like I explained, you need to make a robot. So what do we have to build a robot? We have the tools, especially the electronics tool. You're gonna have a small computer called microcontroller. It's a small computer which we're gonna program using C++, or programming language, which is gonna connect. So we have the controller, we're gonna program it using C++, using Arduino IDE. Arduino IDE is a software. We're gonna use it to control our microcontroller. And we have an Android app called Remote XY, which we're gonna use to control the microcontroller wirelessly. What are we gonna use? We're gonna use Wi-Fi. How can we wireless control anything? There are multiple ways to do it. One of the first ways that was invented was radio, using radio waves, radio frequencies. Nowadays, we have Wi-Fi, we have Bluetooth. There are other possible ways we can do it. We'll talk about what are our options and why you should choose the following. Most of this workshop, I'm going to lay down multiple options and some of the things you should do, some of the things you shouldn't, do's and don'ts. But at the end of the day, it is an engineering competition. It's up to you what path you choose to go. Right. So you all have been handed your kits. Again, if you haven't, talk to the organizers if you haven't received the kit. In the kit, you have received a microcontroller, especially ESP32. It's a type of microcontroller which supports Wi-Fi and Bluetooth. Then you have received another electronic component. An electronic component is just a component which is controlled electronically. Electrical component, as simple as that. So, like an example, what is an example? An LED light is electronic component. A doorbell, the speaker is electronic component. Here we have a component called a motor driver. Basically a component that controls motors. How does it control motor? It controls motors using programming. You can program the behavior you want out of motor using a motor driver. You have two motors, two DC motors. You have heard of DC AC, direct current, alternating current. You have two DC motors. You have 4 AA batteries, which have been given to you for testing. Fair warning, you will run out of the juice in the 4 batteries. You might need to buy your own. You will get further 4 brand new batteries at the day of competition. But so far, we have started you off by giving you 4 batteries to power the robot. And you have wires and breadboards and caster wheels and other miscellaneous components in your kit. All right, so what's the outline for this workshop? We're going to talk about the electronics, the microcontroller part of it. Then we're going to talk about basic programming concepts. Now, this group is a mixture of beginners, intermediates, and some expert 3rd year, 4th year students. This was advertised as a beginner competition. So the goal is to understand all the basics of programming as far as you need them for this competition. So we're going to go over really basic concepts. For some of you, you've already used them or you already know them. But for most of you, you haven't. That's why we're going that low level, that basic. And we're going to slowly build our understanding of how do we use programming to get the job done. Next is the whole aspect of motor controlling. How do you use that electronic component paired with the brain, which is our microcontroller? How do you use it to control, to get whatever we want out of our car? A car is a vehicle that needs to move. It moves due to the rotation of wheels. So basically, if you want to move the car, you need to move the wheels. Wheels, motors, same thing. So it's clear part of the logic why we're controlling motors, because they're going to make our robot move. And after all, we're making a RC car. We're We're making a remote control racing in this competition. And last is the whole wireless control aspect of it. How are we gonna control it wirelessly? Fair warning, the last part is a bit advanced, but I'm gonna make sure we have broken it down to its bare bones. You don't need to understand how the actual programming works. You just need to know how to use it. All right. So let's start with the basic. What is a microcontroller that has been given to you? We're gonna go over this fairly quickly, but there are two types. There are multiple types of computers. The most basic computer is an integrated computer chip, which you're familiar with. The CPU chips in your laptops, in your computers. Intel, Mac, whatever, the chips, they're big, they are computers, CPUs. But they are very big and very bulky. There are also other types of chips. For internet, there are chips. For different types of chips for different types of purposes. Nowadays, you might have heard of all of the AI chips that have been in the market. So we also have microcontrollers. What's the difference? A microprocessor looks something like this. It has a structure. You don't need to understand all of this. It's just, I'm giving you introduction to a lot of different fields and topics just to spark your curiosity and your interest. The important things, I'll press on them a little more. Microprocessor, like a laptop CPU or a PC CPU, versus a microcontroller, which is bare bones broken down into very basic components for very basic logic. It's very power efficient, and it cannot do as much as your CPU can do. Your CPU can do a lot of work. You can have 50 tabs open. You can have a lot of things running at the same time. Microcontroller is very simple. All right, why are we using ESP32? Almost all of you guys, if not, have heard of the word Arduino. You've heard of the alternative of ESP32, which is Arduino. There are also other types of microcontroller, STM32, Arduinos. There's a whole market of it. Why are we using ESP32? Because it's the most cheap and it's the most bang for buck. It's not the most cheap, it's the most bang for buck. With $3 of $3, you get all of the capability of an Arduino, plus Wi-Fi, Bluetooth, and other features that you don't need to concern yourself with, but it's a really big deal. And also, we chose the chip considering that you might use all of the components given to you in future projects. So this is a beginner-friendly chip, just like Arduino is. Arduino lacks the support for Wi-Fi and Bluetooth. And the competition, we wanted to make it wireless control. All right, another concept, analog versus digital. Show of hands, how many of you are not related or not in computer, electrical, or software field? You're not in those fields. All right, fair chunk of people. Because if you're in Cohen elect field, this is your first year courses. You get familiar with these concepts pretty easily, even if you haven't. Big difference is analog is continuous, digital is discrete. Now, words again, what is continuous, what is discrete? The point is, in real life, everything flows. Imagine a river flowing. A particle in a river is going from point A to point B continuously. There is no breaks in its path, in its flow. Whereas once we measure, anything that we measure is discrete. We're measuring 50 times a second, 100 times a second, 2,000 times a second. However much accurate we get. We are measuring at certain frequency. So it's not continuous, it's discrete. It's getting to us in chunks. Basic concept. So another way of putting at it is, let's say electricity, basically electrical signals that you get, your Wi-Fi, your Bluetooth, everything. Radio waves, they travel continuously because they are a wave, up and down, up and down, up and down. But once your phone's transceiver gets those waves, if it needs to process anything, the word digital, if you remember, we are living in a digital age. Everything is digital. Your computers are digital. What does it mean to be digital? Digital means ones and zeros. You're dealing with numbers. You're dealing it segment by segment. Analog means there is no number, there is a range. In computer terms, digital means ones and zeros. Binary, 0 or 1. All of you guys have heard computer talks in digital. Whereas the actual value, analog means anything in between. Digital means either 0 or 1, on or off, yes or no. Analog means anything in between. To give you a practical example, let's take two sensors. Let's take a temperature sensor. A temperature sensor gives you a reading from whatever range it is, but it gives you the reading. The range of the temperature sensor, for example, is 0 to 100 degrees. So it will give you any value in between two. Let's say outside is 30 degrees Celsius, it will give you 30 degrees. But let's say now we have a door sensor. A door sensor is simple, on or off. Is it on or is it off? You don't care about anything in between. There's no point. Is it on or is it off? So on or off, digital. Anything in between on and off, analog. All right. So another concept. Now we pair it with input output. Input output, the most basic concept. Everybody's familiar with it. But what does it mean to be digital input, digital output, analog input, analog output? Digital input means you are getting the value on or off. That's it. That's all you're getting. Digital output means you're giving somebody command, or you're giving an output on or off, 0 or 1. That's it. Analog, like I explained. What does analog mean? If you're getting an analog input, it's going to be a certain value from 0 to 1. It's not going to be 0, 1. It's going to be 0.2, 0.1. It can be 0 and 1 too, but it's also going to be values in between. Same thing goes for analog output. What is analog output? Let's say you're controlling something. Not going to just give it 0 or 1. You're going to give it anything in between two. All right. There are some other examples. So just to visualize this concept better, we have an infrared sensor. Basically, you can consider this as one of the door sensor or occupancy sensor. In most of the Concordia rooms, you have realized that there are motion sensors. If you walk in the room, it automatically lights on. That's an example of a digital sensor. That's exactly what the sensor is doing. If something is in between, it captures it, gives you a 1, gives you a high. So another thing, 1, 0, on, off. In the world of computing, we also refer to them as high and low. Low means 0, no. High means 1, yes. Whereas analog outputs, we'll go over this technology PWM a little more in detail later, but analog output is represented in a way in a format called duty cycle, a percentage of the signal. Let's say you're sending 50% of voltage, that means you're sending 0.5 as an output. The value as an output. We'll go over it in detail. But just to show you the difference, this is just high and low, whereas this can be anywhere from, so the first image is 0 volts, the second image is 5 volts. That means low. So now you also understand what does low and high mean. In terms of voltage, low voltage means low voltage, high voltage means high voltage. Phi is higher than 0. So first one is 0, low, the last one is high. And now analog output or input is analog, is everything in between two. All right. So how do you, when it comes to analog input and analog output, how do you convert them from one to another? In computer work, everything that is happening in your computer is digital, is ones and zeros. So if you're getting a digital input, is ones and zeros, you don't need to change anything. It works. But now if you're getting an analog input, you need to convert it into digital for a computer to work. Computers are digital. How do you do it? You do it with something called PWM, pulse width modulation. You don't need to remember the concept. You don't need to understand what's happening. You do need to understand what's happening, and you need to know how to use it. We'll get over the usage later. What's happening? There's a pretty nice visualization of, you are saying, let's say I have a distance sensor. The distance sensor will give me as an output a distance, right? The sensor, the actual sensor doesn't give me a number. Let's say the range of distance sensor. Distance sensor is same as temperature sensor. I'm just using a different sensor to give you different examples. There is distance sensor. Its range is from 0 to 100 meters. The sensor is not going to give you the number 0 or 100. It's going to give you a voltage reading. It's going to give you 0 for 0 meters, and it's give you 3.3 volts for 100 meters. So let's say you're at 50 volts, it's going to give you 1.53, whatever, 57 in the middle. So, but now, how do we convert? So you get this point. Now I'm talking about analog input. A sensor is giving you input. Let's say now you want to control a brightness of an LED. How do you turn on and off an LED. 0 means off, 1 means on. So far, the logic chain is unbroken. 0 means off, 1 is on. So if you want to turn off an LED, you just say 0. If you want to turn on an LED, you just send an output saying 1. So far, did anybody notice how a sensor is an input device and LED is an output device? Same way, a motor is an output device. A joystick is an output device. Whereas your computer needs to your computer is it needs both input and output device. Computer is the one that manages your input and your output devices. So an LED is an output device. You want to turn on and off, just do the digital output 0, the digital output 1. Let's say now you want to control its brightness. Now you do analog output. And once you say, give me 50% brightness, what it will do is it will, using PWM, it will say, it will give on the line, on the wire, it will give 1.5 volts. Again, the range is from 0 to 3.3. If you say, give me 50% brightness, it will, on the line, it will give 1.5 volts, which equates to about 50%. This is how it gets simulated into actual 50% value. There is no device which will just take the voltage up and down. Try to imagine a voltage in a wire as a level. It's 0, it's a low level, or it's high, a high level. And with your hands, you're pushing it or pulling it up and down. You have a low level voltage, you have a high level voltage. And with your hands, you're pushing or pulling it up and down. In reality, that doesn't happen. How do you simulate change in voltage? Using a method called PWM. As you can see, as the duty cycle increases, the voltage increases. As the duty cycle decreases, voltage decreases. What is duty cycle? The amount of time it stays on versus the amount of time it stays off. So let's say if it stays on for 50% and it stays off for 50%, that means 50% of the time is off. So you're only sending 50% worth of voltage. And it's doing it so fast that you're basically simulating a voltage. That's why you might have heard that LEDs, fluorescent LEDs, they flicker. If you take out a video camera, if you try recording most of the LEDs, they flicker. Because in real life, they are flickering, but they're flickering so fast that you don't really, your eyes cannot recognize it, but your phone cameras can. Same concept is applied there. Why is the LED blinking? Because it's going on and off so fast that you cannot see it, but because of it going on and off at a certain frequency, it can simulate a certain brightness. So if I give 50% voltage, the LED will be 50% bright. If I give 50% voltage, the motor will spin at 50% speed. If I give 100% voltage, the motor will spin at 100% speed. 0, it won't spin, it will stop. So now you have a working understanding of how voltage is related to physical things like speed or brightness. This is the world of electronics. How do you control everything? Luminosity, speed, motion, everything with electricity. How do you convert electric power into mechanical power or chemical power? How does that happen? There are methods. All right. Basically, what I explained, you imagined, now you're seeing it. What's happening is the same thing. The PWM is going from up and down. But let's say now you want to change the brightness of the LED to 75%. You're going to do analog output 75%. You say that? Once you say that, the actual voltage in the wire is going up for 75%, down for 25, up for 75, down for 25, and this is basically going to simulate 75% of the total voltage. So your LED will be now 75% bright. All right, another concept, logic versus power. So far, we talked about input and output, analog input, analog output. All of those are a type of logic. Logic means, in computer world, logic means signal, data. And power means you're powering something, battery. If you think about logic, think about signal. If you think about power, think about batteries. Your motors, they need to spin. Your LED, they need to shine. They need to glow. How are they glowing? They are converting electrical power into something. How do you get that electrical power? Batteries, plugging it into sockets, powering it from your laptop, which is powered by a battery. So at the end of the day, it's either battery or a live source of electricity. That's how you're converting the electrical energy into another type of energy. For example, for motors, you're converting electrical into mechanical energy. That's the power side of it. Logic side of it is how you're sending the data. That's the ESP32 side of it. It's a computer at the end of the day. It's sending and receiving data. So we have to deal with, and both of them are happening using electrical wires. They are both electricity. Your ESP32, everything that is logic related is working on 3.3 volts. From 0 to 3.3 volts. So 3.3 volts means 1, means high, means on. You get the logic. 0 volts means 0, off. This is the demonstration of your logic. But power is different. Your motors are 9-volt motors. Your motors take more voltage and power because your motors actually need more power. The microcontroller ESP32 does not need it. For your voltage, your motor, if you have a speaker, for example, if you have LEDs, again, if you have, what else can I think? Anything that requires power, you need to give it power separately. You cannot give it from the microcontroller. The microcontroller only works with 3.3 volts. For your motor, they work on a specific voltage. It can be anywhere from 6 volts to 12 volts, anywhere from between. But it's not the voltage the ESP32 logic works at. The ESP32 logic works at 3.3 volts. Anybody, any doubts so far? All right. So, like I said, the L298N is a motor driver. It's an electronic component that is going to control your motors. It is the thing that is going to convert your logic, your signals, your commands from your computer. Your computer is going to command this device, and this device is going to control the motor. Because the motor is working on a different voltage, your logic, your computer is working on a different voltage. So you need something in between that can also control motors, but they can also listen to the controller, to the computer. That's where the motor driver comes in. What the motor driver is doing, it's taking commands from your computer. Your computer is signaling it. Your computer is controlling the motor driver. And then based on the commands, start, stop, spin at this speed. Spin one motor, don't spin the other motor. These are all the commands given by your computer to the controller. Based on those commands, the controller, L298N, is going to control the motors. It's going to convert the logic into power. So this is the red thing in your box, in your package. This is the motor driver. Electronic-wise, so like I said, it's a black box where one side it takes logic, and other side it outputs motor commands, motor voltages. And from the examples before, like I explained, how do you control the speed of a motor? By changing the voltage. How do you control the brightness of an LED? By changing the voltage. So here, this little piece of electronics is changing the voltage of the motor based on whatever command, logic, ones and zeros, it is receiving on these wires from the computer. It receives commands from the computer on these 4 to 6 wires, and then it converts them into the 2 motors. So this motor driver at any given time can control 2 motors at the same time. There are different types of motor driver. One motor driver can only control one motor. One motor driver can control 10 motors, depending on the type of motor driver. This motor driver, just the way it's configured, can control 2 motors at the same time. You can name it motor 1, motor 2. You can name it motor left, motor right. Your choice. The motors are connected here. The logic is connected here. Does anybody see if this works? This will work. You're getting input into these wires, and your motors are connected here. Will this work? Go on.
No, because you Power.
Very good, 100%. If you guys didn't realize it, what you missed is the power. This controller is outputting to the motors. Again, motors are output device. They're not input device. They're output device. This controller is outputting voltage to the motors and is taking commands from the microcontroller. Or where does the power come from? You still haven't powered the motor. The motors are not going to work with this signal, because these are logic signals. These wires are for logic. They're not for power. So you have separate wires. These two wires here, and they're there for power. They are there to power your motors. These wires are there to control your motors. Logic versus power. There's a better demonstration here. If you guys can see, this is in electronics, most of the terminals, most of the pins are named. They have a name. We're going to get into the details of that later. But just to visualize, you have two motors. We're going to name them output 3, output 4. And here, we have two outputs again. Output 1, output 2. Output 1, output 2, output 3, output 4. One is positive, negative, because motor has positive, negative wires, red and black. Red is usually positive. It should be 99% of the time. It should be positive. Black should be negative. And you have E and B in 4, in 3, in 2, in 1. These are all logic wires. These wires are going to take care of logic, of signal, of command. These wires are going to take care of outputting power to motor. Where is the input power? The input wire comes from these wires. There is a 12-volt line. That means you cannot connect anything that is greater than 12 volts. If you connect anything that is greater than 12 volts, you will burn the component, because it can only take 12 volts. And you have ground. In electronics, electricity, you always have a positive and negative. Closed circuit versus open circuit. Closed circuit means it's closed. That's the only way electricity will flow. So in any component, you need to connect the positive and the negative. Negative here means ground. Everywhere ground means the negative wire, the black wire. Positive means the 12-volt wires. And the power. So power comes here, leaves here like this. It's going to be a loop. This is to power the motor driver itself and to power the motors. If you guys notice, there's also a 5-volt line here. Just to let you know, this is not input. This is input, this is output. So just the way the motor driver is built, if you give it 12 volts, it will power the motors, it will power itself, and it will also give you power at 5 volts. It will convert 12 volts to 5 volts internally. For itself and for you too, if you want to use it for something else. So this is how it's going to look like. This is basically 100% how your electronics design, as far as this competition is concerned, is going to look like. Very simple electronics. You can count the wires on your hands. There's motors connected to motor terminals, power connected to the power terminal, and signals connected to the microcontroller. We'll talk about the signals and the pins later, but your microcontroller, your computer is connected and is powering. That's it. This is the electronic part of it. Don't bother taking pictures. You're gonna get the slides and all the code and everything later. So, computer, motor controller, motors, all the wires. In this diagram, you can also see you are powering, in this diagram, we are powering the motor driver with the 6-volt power supply. Why does it show 6-volt power supply? I said the motor driver can take up to 12 volts, but it can take up to 12 volts. The lower voltage you give, the slower your motors will spin. Because like I said, how do you control speed? By changing voltage. So let's say if you give a motor which is rated for 12 volts, if you give it 12 volts, it will spin at full speed. If you give it 6 volts, it should spin at half speed, because 6 is half of 12. Just the way we have designed this competition, each one of you has a 4. Wait. Do you have a 9-volt battery or? Oh, yeah, you have 4 AA batteries. 4 AA batteries. 1 AA battery is 1.5 volts. 4 AA batteries is 6 volts. And this is one of the rules of the competition. Yes, if you use a higher power battery, higher voltage battery, you will get a faster robot. But the constraint is an engineering competition after all. Engineering comes with constraints. One of the constraints is 6-volt battery. Everybody has 6-volt battery. The robot design is on 6-volt battery. So everybody's max speed is actually the half speed of the motor. But that's required for both safety and control and other reasons, but 6 volts. So you're gonna give motor 6 volts, and based on those 6 volts, you can also power the ESP32. All right, next, this is not a piece of electronics, but really used in digital systems and electronics. Breadboards. All of the Elec 1 people should already know what a breadboard is. For those who don't, breadboard is just all of you have been given breadboards. Breadboards is just a piece of plastic inside of which it has metal rails, and just the way it is, the metal rails, these are the metal rails, this is the plastic, the white is the plastic on top, but underneath the metal rails are connected. So these are called female pins and male pins you have on your ESP32 or your wires anywhere. Plug and play. These are solutions for you to experiment with the electronics, with the wires that have been given to you. You just plug, it's snap fit, everything is snap fit. You plug your controller here, you plug the wires here. And the thing you need to remember is the last 2 columns are connected vertically, and everything is connected horizontally, like this. So these 5 dots are the same thing. They're representing a wire. They're the same thing. So if you give 5 volts at this dot, all of this rest of the 4 dots has the same voltage. If you give signals, let's say you connect a sensor in this dot here, whatever the reading the sensor is giving, whatever measurement the sensor is giving, the rest of the 4 dots have the same measurement, same reading. Same thing happens here. If you connect something here, every other dot in that specific column, you can see they're connected. They're basically metal wires. So if you touch a wire, now the electricity is flowing through it. So, same concept, everything here is connected, everything here is connected. Why do we have vertical and horizontal lines? The vertical lines, when I say vertical, I mean the long ones, the 2 bars at the end, are for power. Plus means positive, blue means positive, red means positive, blue means negative. Usually it's sometimes black too, but red is always going to be red. Positive, negative. So if you connect power, let's say you connect power for all your sensors, all your motors, every power is here. All of these rails has power. That means you can connect multiple sensors, multiple electronic components, and you can power them using just these 2 wires. It's in this workshop, unfortunately, just the scope of the challenge is so big. There's going to be a lot of concepts thrown at you. I don't reasonably expect for you to understand each and every concept, but you need to at least see them or get interested by them, because all of these tools are required for you to have a successful robot in this company. All right. We will also talk about this exact slide at the very end once you have more perspective. But so far, the reason the slide is here is so many concepts thrown at you so far. Let's make it a little bit intuitive. Let's make it a little bit interesting. This is, or something like this, is what you're going to make in this competition. It's going to look something similar. Same wheels. This is a 4-wheel design. You guys don't have 4-wheel. Everything here is proof of concept. After the workshop, you can take a look. They all work. We will take them for a spin. The point here is you're going to have motors, wheels, you're going to have controller, you're going to have the motor controllers, the wires going everywhere, and you're going to have a design. Now you need to make, this is the mech part of it. You need to make the actual robots. How are you going to stick everything? Hot glue guns. We could not reasonably give each and every one of you hot glue guns, but hot glue guns are very cheap in Dollarama, and there are multiple clubs, associations, hall building rooms where you can get hot glue gun. Hot glue gun is one option. Another option is tape, super glue, any other way you can think about sticking to things. The point is you need to make a car. The wheel needs to be on the bottom. There needs to be some sort of base where every other component sits on top. You need to make sure the wires don't dangle in the wheels, otherwise it's not going to move. And it needs to be a package of its own. There's not going to be a cable plugged into it. It's going to have the power, the battery in it, It's going to have the brains in it, and it's going to have a way to move, motors in it. It's a complete detached package. It's not going to be physically attached to anything. And you're going to control it wirelessly. One of the options for you to make your chassis is foam boards. You cannot see it here, but this piece of thing is a foam board. You can get cheap foam boards, Dollarama. You can get thermal boards. There are different types of things. $1 a piece, very cheap construction material. This is an engineering competition. You need to create your own design. You need to take into account turning radiuses, speed, weight, all the other dependencies and requirements you can think of. You need to account them all in your decision-making process of how you make this robot. Another option is, of course, you can use a cardboard. There's foam board, there's cardboard. If you make something on a cardboard, it will look something similar. You have a place for battery, you have a place for breadboard, you have a place for your controllers and sensors. There are no sensors in this robot, but in this example, there are also sensors. The point I'm trying to make is the only thing you're constrained is a 6-volt battery, 2 wheels, you cannot have more wheels, 2 wheels, and it needs to be wireless control. Everything else, breadboard is not required. If you can solder or if you can tape your wires, feel free. Breadboard is not required at all. Sensors, there are no sort of sensors required. Not that they are in your kit, but nor you should add. You need to make a robot with the tools and the components provided to you, and a little bit more. The building, the construction material is up to you. You can choose whatever. There's also another option of 3D printing something. If you know your way around modeling using Tinkercad, AutoCAD, Fusion 360, and if you're comfortable with 3D printing something, feel free to use 3D printing. The point is construction material and your design, your call. Electronic-wise, all you need is the brain, motors, and wireless control. 3 things, 3 requirements out of this competition. All right, let's move on to programming basics. This is going to be for people who have no introduction or no familiarization with programming. There's going to be a lot of concepts thrown at you in a very short amount of time. For people who are familiar with programming, this is nothing. This is the most easiest stuff. So, what are you going to use? You're going to use Arduino IDE. It's an IDE, Integrated Development. Environment. Thank you so much. It's basically an app. It's a software on your laptop. What does this software enable you to do? It enables your laptop to talk to and to program your microcontroller, your ESP32. You connect it using a wire, and now you can talk to it. You can get readings from it. You can command it, or you can just program it. Basic conceptual understanding. Programming, all the writing code, is going to be done on your laptop. You don't program on the ESP32. You program on your laptop. You compile the code. You convert it into machine code. What is machine code? Zeros and ones. Computer runs on machine code. Human runs on language. C++ is basically English language. You can understand it. A computer cannot understand it. So the software, compiler inside Arduino IDE will convert the C++ code that you write into machine code, and that machine code is uploaded into the ESP32. All right. This is going to be a big thing. We are not going to go over all of it, but basically there is a little bit of issue that comes with the ESP32. ESP32, if you guys haven't used it already, they're not supported by Windows, or usually Windows, but sometimes Mac and Linux laptops outright. They need a driver installed on your laptop for your laptop to be able to recognize the microcontroller. What is a driver? A driver is just a piece of software that sits on your operating system, and it can do whatever. It can let the operating system do some things. For your laptop, your operating system, to communicate with ESP32, you need to install this specific driver. There is a step-by-step guide on how to do it. If you scan this QR code, it's going to be there. If not, I unfortunately did not put the link here. I will update that. There will be a link here too, so you can just click it and you can go to that page. I have written the step-by-step guide. Basically, for those of you who have never connected to an ESP32, you need to do this setup only once in the beginning, and then you will be able to connect to it. There are 2 steps on the slide. First, if you haven't already installed Arduino IDE, you need to install Arduino IDE. Of course, it's just an app. Just Google it, find the download file, install it. And then there is this driver. Driver, also same thing. It's on a website. Download it, install it, run it. The driver is there. All right, let's jump into programming. How many of you guys have not programmed at all in your life? That's fun. Usually I see some hands, there's no hands. So all of you guys are familiar with programming a little bit. In your high school CJEP, first years of programming classes. So since there is not a single person who is unfamiliar with programming, I'm going to fly through this. We are crunching time. But the point I'm trying to make is just basically trying to revise a bunch of concepts that you're going to use. All right, variables and data types. In programming, we need to define certain data structures, data types, and how do we store them inside computer. What is a variable? A variable's shortest definition is it's a small storage in your computer. Your computer has memory. Storage, ROM, SSD is a different thing. Memory, RAM, different thing. Basic computing, you should all know. RAM. Once you run a program inside a microcontroller, most of the program is stored in the RAM. Now, inside the RAM, what does variable let you do? Variable, based on what type it is, it lets you reserve a small chunk of memory for you to put certain data into it. That's the basic definition of variable. Now, variables are of different types, which are called data types. You can have integer, floating points, arrays, strings, characters. The reason they are ordered this way is numbers. First of all, you can have integers or floating points. Integers means whole numbers, negative, positive, anything in between, 0 to 1. Minus infinity to plus infinity. Any whole number is integer. Floating point are decimal numbers. Numbers with dots, decimal numbers. These are the 2 main types of variables you will be using. This is the second most important variable, which most people don't use it, but it's really powerful if you know how to use it. It's called bool. Boolean stands for Boolean. Boolean, again, it's the same thing as true or false. Digital operation. Is it on or off? Is it true or is it false? Bool is a type of variable which only stores the value true or false. And then we have byte long characters, strings, other stuff, which you won't be using much, but they are there. This is just a refresher on your programming concepts, since there is nobody here who actually don't know any of the programming. Functions. What are functions? Functions is how you get something done. Function, it's basically like a math function. In a math function, you can have x equal to something, something, something. Y equal to something, something, something. Once you solve the equation, you get the value of y. Same thing here. Function defines certain variable. It does some operation, math, read and write, update, whatever it does. Once the function is done, it outputs something. It can also not output something, but that's the thing. Function runs. Function is what you call. Data type, variable, is how you store something. Function is what's running, what's doing certain job. All right, these are the main functions that you need to use for this competition. Let's give you a refresher in all of this. Why are you using Arduino IDE? Arduino is not a programming language. Arduino is a is using C++. But it has given you certain functions and certain data types which makes your life easier programming embedded devices. ESP32 Arduinos are all called embedded devices. Arduino IDE makes it easier for you to communicate electronics and embedded systems. What are some of the functions that Arduino IDE gives you? One of them is called pin mode. Now, as you saw before, every microcontroller comes with pins. That's how you communicate. These are the input-output interface of a microcontroller. This is how the signal electricity goes in, signal electricity comes out. Each pin can do input and output both. Some pins are power pins. They don't do input-output signal. For example, these two pins and these two pins, there is no signal there. It's just for power. It's just to power the controller or take power from the microcontroller. Rest of them, they do input-output both. So you need to, every single time, you need to tell your controller that this certain pin is going to be an input pin. Certain pin is going to be an output pin because that pin is only going to output. Certain pin is only going to input. One pin can only input or output at any given time. It cannot do both input and output. It doesn't work. For simplicity reasons, it can work. For simplicity reason, Arduino doesn't let you do it. Either input or output. How do you define if a pin is going to be an input or output pin? You use the pin mode function. You do it once in the beginning. You tell the microcontroller that this pin is going to be either input, all caps, output, all caps. Either input or output. Digital write is a function that outputs a signal. What sort of signal you might ask? Digital signal. This function, once you give it a pin and a value, it will put that value inside of the pin. What does it mean? Let's say you want to turn on an LED. An LED is connected to pin 23, random example. How are you going to turn on the LED using programming? You're going to tell the microcontroller, digital write pin 23, high. That's going to turn on the LED. Digital write pin 23, low. That's going to turn off the LED. Digital write. Now you have the door sensor we talked about earlier. A digital sensor. Is the door on or off? Is it high or low? Same thing. The sensor is connected to pin 20 this time. So what we're going to do is digital read. We're going to read this value in the connected to the pin. The sensor is sending some voltage reading on the pin. We're going to do digital read. We're going to get either on or off, high or low. Same thing applies for analog domain. Let's say we want to control the speed of motor for our thing. Analog write, the pin. The pin is the PWM pin, the motor controller pin. The pin is, let's say, 19, for example. So you're going to do analog write 19, and you're going to give a value between 0 and 255. We're not going to go into detail why it is 0 and 255. What you need to know is 0 means 0, 255 means max speed. So if you give 100, it's going to be 40% speed. If you give the middle of 0 and 255, it's going to be 50% speed. So if you do analog write, the number, the pin and the number is going to send the output of that pin. Same thing applies for analog read. For this project, you don't need analog read because you don't have any sensors. You're not reading. You're communicating with your phone through Wi-Fi. It's a different thing. There is delay. You're going to use this a lot. Delay just says stop whatever you're doing for certain milliseconds. Let's say if I want to blink the light on, I do digital write 1 high, delay 1000 milliseconds. Digital write low, delay 1000 milliseconds. On for 1 second, off for 1 second. And this will just keep looping. It will just keep blinking the LED on and off, on and off, on and off. All of these commands, if you look, they are serial commands. Long story short, what it means is your laptop is connected to the microcontroller serially using a wire. If you want to start, begin means start a connection between microcontroller and laptop. If you want to print something to the laptop, or if you want to just check if something is connected, serial dot the command. Let's say you're getting a sensor reading on a microcontroller and you want to see it on your laptop. You do, the microcontroller is going to get the data and is going to store it in a variable called data. Data can be of any type, integer, float. But if it's a sensor value, if let's say if a temperature, it's going to be a float because the temperature is going to be 24 point something, blah, blah, blah. So it's going to be a float. Data is of type float. Now you want to see what's the data. What you're going to do is going to print, serial print data. And on your laptop, you can see what the microcontroller is getting from the sensor. What's happening here? Sensor is giving a voltage reading. Your microcontroller is converting it into numbers, into actual temperature reading. And that is what is sending you on your laptop. Again, serial prints is the most important command for you to debug anything. If you want to see if any signal is coming on your microcontroller, or what are you outputting? What speed are you outputting when you control something? Serial print. But again, your actual robot is going to be wireless. So you're not connected to the microcontroller through any wire. It's all wireless. So serial print won't work. All right, conditional programming. If and else. If something happens, do this. Else, do this. You would need if else. Let's say you have in your phone, you have a joystick. For example, you have a joystick controlling the car. If the joystick goes forward, the car goes forward. If the joystick goes backward, car goes backward. Same thing. If joystick forward, car forward. If joystick backward, car backward. All right. Most of your C++ program are the only way a program is C++ program, it has the main function, int main. As long as you have int main, it's a valid C++ program. A valid Arduino program has these two things. A void setup, a void loop. This two function defines an Arduino sketch. What's the difference? The setup will only run once. Once the microcontroller is powered on and it starts, it's going to run whatever you say to run in the setup function. It's going to run it once. And then it's going to go to loop, and it's going to keep running loop again and again. It's going to start from the first line, end on the last line, and once it's end, it's going to go back to the first line. It's going to keep looping again and again and again till you turn off the microcontroller. So setup only one, loop keeps looping. All right. So that was Arduino sketch. Now we're talking about loops in programming. In programming, you also sometimes inside your loop also you might want to keep looping for some reason. There are reasons. There are two types of loop, for loops and while loop. Pretty similar. Difference is for loop checks the condition, both of the loop checks the condition every single time before running the loop. For loop has this syntax and it checks the condition, and until that condition is met, it's going to keep looping it. They are both doing the same thing. They are looping until certain condition is met. But for is more controllable. You can have a variable, you can set it to certain numbers, and it will only loop until that certain number. Whereas while will keep looping. There are two different ways of doing the same thing. Programming-wise, one is better than other. For is better than while for a reason. But your loop, your void loop, is a type of while loop. It will keep running no matter what. Right. If you want to try more examples in Arduino IDE comes with pre-built examples, pre-built code for you to slowly start learning. One of the examples that you should do, and if you want to start, if you're a person who's starting in Arduino, try a blink sketch. What is a blink sketch? Turn the LED off for 1 second, turn the LED off for 1 second. On and off, using programming. What LED? You say you haven't provided us with any LED. There is an onboard LED on your microcontroller. The microcontroller has one, it has two, but it has one controllable LED for you. You can play with that LED. You don't need any other electronic components. All you need is the microcontroller connected to your laptop. So, you need to install Arduino IDE. Don't forget to install the drivers. And then you need to follow the steps in the GUIs shown here. You need to go to the examples. Once you do that, you have a bunch of examples available to you. Now we talked about the function serial here. Serial.begin, serial.print, serial.available. What does it mean? I said the microcontroller is going to output to your laptop. Where are you going to see it? We're going to see the output. You're going to see the output in something called a serial monitor. So far, it's logical. You have connected the microcontroller to your laptop using a serial wire, using a serial protocol. The functions we are using are serial.begin, serial print, serial available. The thing we're going to check is serial monitor. Serial monitor, as the name suggests, is monitoring the serial connection. You have a serial connection between the microcontroller and your laptop. This piece of software built into Arduino IDE is checking what values are showing up. So if you use a print statement, a serial print, this is where it's going to print. So these values are coming from microcontroller to my laptop, and I'm reading them. How do you get to serial monitor? 2 ways. Graphical user interface. You can just go to Tools, Serial Monitor. Keyboard shortcut, Control-Shift-M. If you click it, the serial monitor will open. If you open Arduino IDE, the serial monitor will not be open by default. You need to open it if you want to check. So sometimes people, beginners, if they have not used Arduino IDE a single time, if they've written the code, they flash everything, and then now they're waiting for the output from the ESP. Not going to see the output unless you open serial monitor. All right. Let's talk about wireless control. So this is where it slowly gets complex in programming. Conceptual understanding, you have been using Wi-Fi for a long time. You guys all know what Wi-Fi is and how we're going to do the control. Programming-wise, it's going to get difficult. So we're going to use pre-built libraries, and we're going to provide you the code. Certain part of your code that's going to run on your robot is going to be provided by us to simplify all of the wireless control part of it. But the actual control logic, the logic control of how the robot moves, what it does when the input comes, is all up to you. Wi-Fi, as we all know, there are multiple ways we can connect a Wi-Fi signal, but it's basically the station mode or the soft access mode. Station mode is there is one big router, like Concordia, your house, you have a router, you have a modem, and all of your devices are connected to a central modem. That's how they get internet. Or you can have a soft access. If you guys remember, you can also open a hotspot. Soft access is the same name for hotspot. You can open a hotspot on your phone, and now you can connect all the devices to your phone. But your phone is getting internet from somewhere else. This is what we're going to use for our project. The ESP32 is going to create its own hotspot, and your phone, through Wi-Fi, is going to connect to the ESP32's hotspot. So your ESP32 is going to be a router, basically, a modem. Your phone is going to connect to its network, and that way they can communicate wirelessly. Or you could also have a router that your phone talks to, and the router talks to the ESP32. That's added complexity, and no need for this. It's way easier. For our application, it's way easier. All right. This is something you should try. It's not important because you don't need to work with any of the Wi-Fi code given to you. The Wi-Fi code is given to you, so you don't need to figure out the Wi-Fi code on your own. But if you're so curious in the future, if you want to do any projects, there are also certain Wi-Fi examples given to you. All you need to do is plug the ESP32, and the ESP32 can scan all the available Wi-Fi networks. And other stuff. You can connect to them, you can communicate to other computers, you can send messages from your phone to your ESP32. One of the really interesting projects, and to be frank, very simple project that we have at IEEE Concordia's lab, is we have a door sensor that lets the information, is the door open or close, onto our website. It is a simple ESP32 microcontroller and a sensor, and all that ESP32 is doing is connected to Wi-Fi and it's sending the data over Wi-Fi to our website. Why do we need it? If you want to know if the lab is open or not, if the door is open, that means the lab is open. If the door is closed, the lab is locked. So basically from our phone, from going through our website, using a simple ESP32, we can get the data. There are thousands of different projects that you can do using ESP32 wireless control and other stuff. There's also a section at the very end going over other projects that you might be interested after this competition. All right. So how is your code going to look like? What is your code? Let's start programming. I'm going to give you basic blocks that they should be there on your program, and rest, filling out the finer details, is up to you. Again, the actual running code for this competition is provided to you. There is one version of code that every team is going to get. This engineering competition does not focus on programming that much because it's a beginner competition. the focus is more on designing something and racing and like electronics and mechanical end of it. But you are free to change the code. The code that is going to be provided to you is purposefully not optimized. It's a very simple code that moves the robot very simply. Straight, turn, that's it. Using a simple UI. We're going to talk about the UI too in the future slides. But a simple controller on your phone, it moves the robot. Very simple. If you want to win, it's not going to be enough. You're going to have fun. You're going to have fun. But if you want to win the competition, if you want to be the fastest car, you need maneuverability. You need to be able to control your robot really fast and really accurately. That you cannot do with the code provided to you. So if you want, you need to pay attention to certain things that you definitely need in your code and rest which you can edit yourself. One of the things is the library. We are using a library called Remote XY. It's a phone app, it's an Android app that lets you connect to your microcontroller, especially ESP32. It lets you connect it, communicate it, control it. They also have library. What are libraries? Libraries are pre-made code. Somebody else wrote the code and you are using their code. There are two libraries we're going to be using. One is called Wi-Fi for us to get the Wi-Fi functionalities. And other is remote.xy.h. These are two libraries. The hash include goes over libraries. Hash define. They go over certain constants that you need to have in your code. One of the things you're going to have in your code, like I mentioned, your ESP32 is going to be the hotspot. You're going to connect to your ESP32's Wi-Fi. That means the Wi-Fi needs to have a name and a password. You can choose not to have a password, but there are 30 teams. Somebody else might be able to connect to your network, or somebody else might accidentally connect to your network or whatever. Password is mandatory. You can keep it simple, so you don't have to, it doesn't need to be complex. It's your own Wi-Fi. The only person who's going to connect to you is your own team. That's it. And a name. Make sure the name is different. Make sure the name is unique. So once you open your Wi-Fi and you scan, this is the name you're going to see. And this is the password you're going to use to connect to the network. Now, like we said, what is an Arduino sketch? A setup and a loop. Setup is only going to run once. Loop is going to keep running. The most basic thing for you to use the wireless control app, Remote XY, is you need to mention these things. You need to mention the Remote XY initialization function that they give you. It's included in the library. You don't write this function. But you need to mention this function in the setup. And Remote XY handler is another function that they give you. You need to have that function in the loop. These are the requirements for you to use this library. Otherwise, you won't be able to use the library. What are the rest of the stuff? The rest of the stuff is, this is my custom function called init pinout. You can have this function. Rest, the only mandatory thing is remote XY init and remote handler. Everything else is your own code. You can have anything you want here. I chose to create a function called init pinout, where I define how my pins are connected and what are the pins. Are the input pin or are the output pin? I chose to write that function, and I only need to do it once. Pin out, telling the microcontroller is this pin input or output, I only need to do it once. So it's going to be in setup. Serial begin. Start a connection between microcontroller and my laptop. Start a connection. They're connected, but you didn't set up a connection. They're just connected and the USB 32 is powered on. But if you want to talk to it, you need to do serial begin. What is this 115200? Don't worry about it. Just use the number. It's just a rate at which you're talking. Keep the number safe. In the loop, you need the remote XY handler and every rest of your code, rest of your logic. I said I made a function called pinout. Is just saying I have these pins. They're either input or they're output. We're gonna go over in detail what is motor 1, all of those pins, the names that you're seeing before output. What are those pins? But in the meantime, these are the names. I made another function called handler. This is something that I made. Instead of writing my whole code, inside the loop function, which you can. If you don't have any experience, please do that. But I have experience. So what I did is I created one function in which the function is handling everything, and I'm only calling that function inside of loop. So I'm keeping my loop simple and clear, readable. So the loop is only calling this function, and this function is taking care of everything. That's why it's named handler. This function is taking care of the Wi-Fi inputs, the motor control, everything. All right. On the subject of motor control, let's start talking about motor control. Programming the motor control. How are you going to control the motors, the motor driver? How are you going to control it using programming, using Arduino IDE? What is that code going to look like? The reason I'm showing you code is the code is provided to you, but if you don't understand what the code is doing, you won't be able to edit your own code, and you need to edit your own code for you to get the best possible control for your robot. All right. Like I said, how do you control the motor? If you want to control the speed of the motor, you do analog write. Analog write means output it. Give somebody, write it. There is no read, if you can see. There is analog write and digital write. What is happening in this a lot of lines of code? If you look at it, actually, they're very simple. The way your motor drivers are, your motor driver has this 6 pins. In 1, in 2, in 3, in 4. Enable A, enable B. What do you need to know? Your enable A is the speed command, the speed input. Enable A, you tell what speed do you want. Enable B, you tell what speed do you want for B. So A is for motor 1, B is for motor 2. In 1, in 2 are the direction control for motor 1. In 3, in 4 are the direction control for motor 2. How are in 1, in like, so now you have two signal that you need to give based on the direction. How is that going to work? It's a little complex if you don't follow the logic, but you don't need to understand it. You can just copy paste this and it should work. But if you want to understand it, what's happening here is you need to do in 1, 0, in 2, 1, low and high. Once you give those commands, that means the motor is going to move forward. Once you flip those numbers, that means the motor is going back. So, if you guys can see, we'll talk about this later. There is in 1, in 2. You can either have in 1, 0, or you can have it 1, and you can either have 0, 1, or 2. If this is the case, it's going to go forward. If this is the case, it's going to go back. Basically, you're flipping them. If the configuration of the both input lines is 0 and 1, the motor is going to spin clockwise. If it's 1 and 0, if you flip that, it's going to spin counterclockwise. So basically, with these 2 bits, what you're doing is you're changing the direction of the motor. And with the enable pin, what you're doing is changing the speed of the motor. So instead of writing analog write, digital write, analog write, digital write, every single time I want to change the direction, I made some helper functions. What are the functions? If you read, the functions are in the red. Forward motor 1. For motor 1, move forward. Forward for motor 2. Backward for motor 1. Backward for motor 2. Now you might ask, why are you controlling 2 motors separately? Why are they not in just one function called forward and backward? In forward, you control both motors. In backward, you control both motors. Why? With just 2 wheels, how would you turn? Go on.
Well, one of the wheels should have a different speed than the other.
Yes, that's turn. Let's say you want to spin.
Well, one of them should be like
Yes.
stop, and the other one should.
So if you have 2 wheels and your robot needs to spin like this, one wheel needs to move clockwise, one wheel needs to move counterclockwise. If this happens, spin this way. If opposite happens, you spin opposite way. That means you need to control the 2 motors separately. So one needs to go forward, one needs to go backward. It will spin. If it goes the other way, it will spin. If they both go forward, it will go forward. If they both go backward, it will go backward. Hence, I have control forward and backward for individual motor. And I also have another function called stop. If I call forward motor 1, my motor 1 will spin. If I call forward motor 2, my motor 2 will spin. If I call forward motor 2, my motor 1 is not going to spin. If I call stop, if you see, stop is controlling both motors. Because stop is to stop. I want to stop. I don't want to control motors individually. I want to stop motors. Stop motors is controlling both motors. And how you do? So here we have the configuration either 0, 1 or 1, 1. If we have 1, 1 or 0, 1, 0, 0, 1, 1, 0, 0, any of these configuration will stop the motor. That's why I have digital right, low, 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 and I'm also giving speed 0. I don't need to do both. I'm doing both. Now, I wasn't satisfied with those helper functions. There were still a lot of functions for me to call. So I made a higher level of helper functions. Optional, it's not needed. I like to keep my code clean and readable. The actual loop that is running, I don't want to see 1,000 lines of code there, and I don't know where to follow what's running. I want to see 2 lines of function. I want to see this function is being called, this function is being called. And if I want to see now what error is coming, I can just go to those functions. And I made these simple functions: forward, backward, left, right. Forward, if you see, spins both motors forward. Backward, spins both motors backward. Left spins one motor forward 1, but it spins the other motor backward 1, backward 2. And this flips it. Backward 1, forward 2. These are the ways you are controlling a physical robot in 2D space using programming. Basically making a brain, a logic brain. If it gets certain input, it can control motors, and with certain configuration of motors, now the robot can move. All right. Another segment is, so far, we talked about motor control. But your robot is an autonomous, it's not an autonomous robot, it's a remote control robot still. It's wireless. It needs to react on your input, on user input. So how does it react to user input? Like we mentioned, conditional programming, if and else. If you get a certain input, val 1 it's just value 1, val 2 is value 2. Value 1 is basically my input for forward. I specifically kept value 1 and value 2. I could have kept forward and backward. But this is another thing about programming. You can name the variable whatever you want and just remember what you named it, and you can use it. For computer, val1 is just a name. It doesn't care. So val1 is representing my forward-backward command. Do you want to go forward or do you want to go backward? We're going to soon see how are you going to control those. What is the UI going to look like? But in the meantime, let's say I have a joystick, an Xbox controller. I'm setting forward, I'm setting backward. That forward-backward joystick is basically storing its data into this variable called val1. Val1 is a variable. Now, based on the conditional programming, if the conditional programming starts from val2, but for the time being, let's say if val1 is greater than 0, plus, go forward. But if val1 is negative, go backward. Same thing with val1. Same thing with val2. If val2, which is for left and right, the values are obviously, if you not obviously, but we're going to go. The values are from 0, negative, positive. If it's positive, you turn right. Yeah. If it's negative, do the opposite, turn left. The values you're going to get from remote XY, the app we are using, are going to be from -100 to 100. So 0 means middle, stop. 100 means full speed. -100 means negative full speed. 50 means half speed, forward. -50 means half speed, backwards. So your code has to take those inputs and convert them into motor functions. We have already figured out the motor control. We have already created helper functions that lets us control the motor. But now when to call them, when to run the function. You run the function based on conditions, based on your input, based on user input. Your robot needs to react to your input. All right, we are at the very last part of our workshop. Smartphone control, the remote control. The app I've been talking about so far, Remote XY. What is Remote XY? Some bloke 10 years ago wanted to do the exact same thing he wanted to do. He wanted to control a robot using wirelessly through his phone. He couldn't find an app. He couldn't find the software. So one day he decided, I'm going to make my own. He made his own. It was open source. He's on charge for it. It's open source. He made the Android app. He made the website. He made all the control. He made all the library, all the code. So you don't have to write the Wi-Fi code. It's already there. And he made a really nice user interface for you to customize your controllers. Remote XY is a website, remotexy.com. You can go to the website. On the website, you can design your custom controller. We're going to go look through some examples of that. And then once you do that, you can generate a code file. That code file is basically going to be this controller, which if you run on your microcontroller and you connect to it on your phone, on the Remote XY app, you need to install an app. It's a free app. Once you install the app, and through the app, you connect to the ESP32, you're going to get whatever gamepad design you did. And now if you control this, the input will be sent via Wi-Fi to ESP32. This way, you will be able to control the microcontroller wirelessly through an Android app. Not Android, a phone app, basically. So, what are the main things you need to realize about a Remote XY? It works over Wi-Fi and Bluetooth. We, for this competition, have decided to use Wi-Fi. But Bluetooth is more power intensive. Wi-Fi is also power intensive, but Wi-Fi is just simpler. It's faster too, for what we want to do. And it's more reliable. Bluetooth is not as reliable. All right, you have wireless protocol, Wi-Fi, that we're going to use. You have means of inputting. You can have buttons, you can have joysticks, you can have sliders, basic gamepad design. You can have anything. And you get the code. You get the code for it, so you don't need to worry about the Wi-Fi stuff. I highly recommend for all of you guys to make your own controller, because the code that is provided to you, it is, like I said, very simple. It's going to work 100% of the time. It is going to work, but it's very simple. It's for those of you who lack experience with programming and actually are not interested in programming, you're interested more in the design part of it or the electronics part of it, you don't need to worry about programming. All right, we talked about this, how it connects. Only the green things are meant for you to change. The rest of the things, you don't change. You keep it as it is. Green is the name of the Wi-Fi that you want to connect to, and other thing is your password. Now we're going to talk about the app interface. The app has other options too. It has switches, it has dials, it has screens, it has joysticks, other stuff. Not useful for this competition. The three things useful for this competition are buttons, sliders, and joysticks. Why? This is something you can design in Remote XY. In fact, we will do something similar in a short while. But this is something I designed on the website. Once I did generate code, it gave me a code. And once I upload the code to microcontroller and I connect to its Wi-Fi, if I go to the Remote XY app, I'll get this on my phone. My phone is connected to my ESP32, and if I open the app, this is what's going to come to my app, because this is what's running on my ESP32. So now, if I click this button, my ESP32 is going to get the input. What to do when the button is clicked is up to you. Why this configuration? The most simple configuration. Forward, backward, left, right. You click on forward, it moves forward. Doesn't care about speed. There is no speed control here. If you click forward button, full speed. Okay. Backward button, full speed backward. Left button, spin left full speed. Right button, spin right full speed. You can click right and forward, and it will do an arc turn. That completely depends on your code, how you do your programming. Sliders, same thing, but now you have speed control. It's not just on or off, forward or backward, left or right. You can have forward with 10% speed, 50% speed. If you dial it all the way up to 100, full speed. Same thing for left and right. You can spin slowly, you can spin really fast. And if you control them both at the same time, you can spin and turn.
Does the app only work for Android?
No, I am not sure, but because I've only used in Androids, but I've seen on the website that it's not Android limited. You can also install it on Mac, on iPhones. If you cannot install it on iPhones using Apple Store, there are other ways to install it on your iPhone. Is there? Is there? Next is joystick. Same thing as sliders, up, down, left, right, but now using just one thumb. So you don't have to go forward and left for you to turn like this. You can control it. You can just go 45-degree angle here, and it will go forward and left same time. Anybody has any questions regarding why do we have 3 options? Any confusion so far? Wonderful. Go on.
Is there any way we can combine joysticks?
100%.
Sliders?
100%. That was my next point. That was my next point. All right. You might ask, why are you even talking about sliders or buttons? Can we not just use joystick and call it a day? It gives me all the control with just one thumb. I don't need anything else. For a robot to move, all it needs to do is get a command for forward, backward, and turn. This gives me both. Everything has their own trade-offs. Here, you have only one control option. It's doing the same thing as sliders, but here only one thumb. So and this is also a more complex to program than regular sliders. So buttons is the most simple, on or off. Digital read, you don't even need to do digital read, but the input you're gonna get in your ESP32 is gonna be either on or off, on or off, on or off, on or off. Go forward, go backward, left, right, full speed. Very simple to program. A little bit difficult to program. You need, so like I said, an example, the input that is gonna, the ESP32, what is gonna receive is gonna receive 0, minus 100, 0, plus 100. That is what it's gonna receive. So now you need to map these numbers to control speed of the motor. Do you remember speed of the motor? How do you control it? Analog right. Analog right works from 0 to 255. The example is already there, by the way, but somehow you need to map the values minus 100 to plus 100 from 0 to 255. You have to do some math. You have to do some mapping. All programming, a little bit more difficult. But here still, you have 2 separate channels of input, like forward channel, forward, backward, or turn channel, left or right. You can still control them individually. If you don't want to turn, you can just go forward. And you know that the slider is only going to control forward. It's not going to mix turn signal with forward signal. Let's come to joystick. Well, joystick, you need to be very sure that your thumb is pulling the joystick very forward, because if it's a little bit crossed, it's also going to have a turn signal. Also, the input you're going to get here is going to be 2 variables, x and y. 0, minus 100 to 100, minus 100 to 100. But still, again, you need to map an array this time of 2 variables into the input that you need for analog right. So that's a little bit of programming you need to do. The code provided to you, now that I think of it, I'm going to provide you 2 codes. I'm going to provide you a code with buttons and a code with sliders. This exact thing, sliders. For you to understand how you can control with buttons and how you can control with sliders. Joystick is up to you if you want to do it. The code goes over how you map the inputs that you get from the app to the inputs required by the analog right function. Because analog right function requires 0 to 255. This gives minus 100 to 100. All right. we're gonna do this shortly, but we're gonna go to Remote XY. We're gonna create our own gamepad. Once you hit generate code, code like this is gonna be generated. What's the red stuff and what's the green stuff? You don't need to know what's happening here, but you do need to realize that this is there in your code, and you need to keep it. The red stuff is the configuration encoded in the numbers. The numbers means the layout of the screen, where everything is placed, what is placed where. This is the code on your ESP32. Once your Wi-Fi runs, your app connects to it, and it follows this instruction. So it's gonna follow the numbers, and based on those numbers, it's gonna put all the buttons and everything on your phone. Once that's happened, it's gonna give you input in these variables. Again, don't be scared by this. This is just a variable type. Your normal integers are 16-bit or 32-bit, depending on your system. Here, they're just 8-bit integers, nothing else. What you need to realize is just an integer. Variable, the names are gonna be what you define on the website. In the website, I defined slider left, slider right. So the variable name here is slider left, slider right. I could have named it variable 1, variable 2. So the variable name here would be variable 1, variable 2. And this is all in a structure. You can see the structure starts from here, and it ends here with the name Remote XY. All of this you need in your code for your phone to connect and communicate with Remote XY app. We talked about it. How does it actually connect? The Remote XY initialization and Remote XY handler. Initialization takes care of the setup of your phone gamepad controller, the UI of it. And handler is going to take care of all the variable setup and getting the input real time. Let me go over once again. Setup only runs once. Loop runs multiple times. So the Remote XY init function is going to set up your layout of your gamepad on your Android phone. This function, Remote XY handler, is the function responsible for real-time getting the inputs from your phone to the controller. Your input, you're controlling the joystick, you're getting certain input. This function makes sure you get the input on your microcontroller end. All right. So on that note, just to show you, give you a demonstration, let's go to Remote XY. A very open source vibe, if I say so. Not at all polished. This is a one-man job. So, you can make an account if you want, you don't need to. Let's go to the editor. You can click start now, you can read their guides. Also, at the end of the workshop, there are a lot of YouTube videos and tutorials linked to it, which you'll also get additional resources in the rule book, which you get sooner, like by the end of this day, hopefully. All of the information is linked there. Let's create an app. So here, the thing, I encourage you to play around, figure it out, and make your own controllers. Or for people who are not making your own controller, you don't need to worry about any of it. The code is provided to you. Just change the motor control part. You can keep the sliders and everything. This is only if this option is only if you really want to make your own custom gamepad with your own colors and whatever you want. What's going to happen is there are buttons here. Let's take a slider. You're going to slide a slider here. You're going to change the size or whatever. And again, if you see, this is not a centered slider. This is an extreme slider. We go either 0 or 1. We're going to convert it into, so this is for vertical, horizontal. It's going to slider vertical, horizontal. The UI is very intuitive, middle. Now the middle is the default. So if you slide the slider all the way to the end and you remove your finger, the slider is going to go back to middle. The other way. Rest of it, we're going to go. There are two things. First, how to use the UI. You can get more information on YouTube or just reading their docs. Another thing is the configuration. Make sure this is your configuration. Once you start a blank project, it's going to ask you for what are you using. You are using Wi-Fi on ESP32 using the integrated Wi-Fi chip. You don't have a separate Wi-Fi chip. The Wi-Fi is on the ESP32 using Arduino IDE. There are multiple options for each option. Make sure your configuration is this: Wi-Fi, ESP32, integrated Wi-Fi, and Arduino IT. And then here is where you mention the name of your Wi-Fi, your hotspot. Again, you can mention it here, or you can just change it in your code, up to you. But whatever you name here is gonna appear in your code. Whatever you name the slider, so here it's slider_0. Now this is gonna be my slider name. C++ programming does not care what I name as long as it's a reasonable C++ name, a variable name. So this works, but I want to be more descriptive. So I'm going to do right. There are no spaces in variable names. It's programming. Right slider. So once the code is generated, this is what I'm going to get as a variable. You can obviously change colors, up to you. That's some font. And here, get source code. Once you click it, you're going to get this code. We already talked about this. All of this is comments. Let me do this. Let me copy this. I opened a random project. I shouldn't have done this. I opened VS Code just so you can see it better. All right. What that code gives you, we already talked about. We talked about the libraries you need to install, the Wi-Fi name. You can change it here too if you want. This is the configuration that you need to keep. All of the code from here to here, you need to make sure you keep. This is the code generated by the RemoteXY app, website. Don't mess with it. If you mess with any of the numbers, the app is not going to work. And like we mentioned, RemoteXY, you need the init function and the handler functions. The rest of your code goes here. Your setup code goes in the setup. Your loop code goes in the loop. This is the format that you're going to follow if you're going to write your own code. You can always save your projects and all of that stuff. And add a joystick, add buttons. If you are on a free plan, which that's all you need, you don't need a paid plan. If it is a free plan, you can only add 5 inputs at a time. So you realistically need no more than 3, but that's fine. So that's the Wi-Fi control part. So far, I talked about a lot of concepts. Any doubt anywhere? Nobody? Wonderful. All right. So after this workshop, what's on your to-do list? These are not in the order. Your basic to-do list, whatever I talked about, at least 25 to 30 concepts. Write down a list. Go over this workshop on your own time, whatever you want to do. You have sufficient time for you to make this whole thing. I personally, this competition is loosely designed on a similar competition that I partook in last year, and we made this robot from scratch. All of the code, all of the electronics, all of the structure in 6 hours. So 2 weeks is definitely more than 2 weeks you have. It's definitely a lot of time. The reason you have that much time is that the expected demographic of this competition is all beginners, first year, second year students. So, and this is an actually complex engineering project. You're dealing with a lot of complex topics that, because you're a beginner, you don't need to know ins and outs of, but you actually need to know how to apply them and use them. So ESP32s, microcontrollers, Arduino IDE. If you're not familiar, open YouTube and just type the thing that you're not familiar with. First, go over the links that we have provided you, but if you go over them and you still don't understand, YouTube. Another thing, electronics. People, if you don't have experience, people who don't have experience with wiring and how power and logic works, open circuit, closed circuit, you need to make sure your wiring is really good. Because if your wiring is shitty, your robot might stop working. Your robot works for the whole time you're making the robot. On the day of competition, it doesn't work because you didn't take care of the power draw, the drain of the current from the batteries. You didn't take care of how much the ESP32 will take. If you don't do the wiring properly, you might burn a component. I explained, the motor driver takes 12 volts. At max, it can take 12 volts. By any means, it's not possible because you don't have a power source more than 12 volts. But let's say you're tinkering, and if anything, you give it more than 12 volts, the component is simply going to burn. You're going to see magic smoke. And in electronics, if you see magic smoke, you cannot put the smoke back in. Once it's out, it's out. Same thing with the ESP32. ESP32 is a 3.3 volt microcontroller. If you try to, you can power it with 5 volts, you can power it with 6 volts, but only power. All of the pins are basically going to take electrical voltage from 0 to 3.3 volts. If you provided 5 volts, you're going to burn the microcontroller. For this competition, you're not going to get another microcontroller. You only have one. If you burn it, we'll talk to the organizers, but you shouldn't burn it. And you might burn it. So make sure you know ins and outs of powers and logic. You're not supposed to connect power wires where the logic wire goes. And if you connect logic wire where power wire goes, also doesn't work. You might end up burning one thing or the other. Another thing you need to take care of is power draw, voltage draw. Once you have a battery pack, 4 AA batteries, 6 volts, it's going to drain. Slowly over time, you're going to use the batteries. That means your 6 volt is, by the end, is going to be 4 volts. And if it goes below 4 volts, the motors are just not going to spin. So if you see your electronics struggling, that means probably your batteries are drained. Buy new batteries, replace the batteries. In the meantime, once you don't want it wireless, once you're trying, if you're doing motor control and stuff like that, you can power the motor from your USB cable straight from your laptop. But your laptop can only provide 5 volts. So the motor will spin very slowly. But you can still get the logic. You can let the motor spin slowly, doesn't matter, but you can move the motor with the voltage from your laptop. Again, I have done this. I should have put the picture on it. I did not. I'll put it when I send you the slides. When this competition was happening, the competition I mentioned, we had the same motor driver, everything. The mistake I did is the robot was powered using battery. The ESP32 was powered using the motor driver, because if you see, the motor driver has a 5 volt output. So that 5 volt output was connected to microcontroller. So the microcontroller, ESP32, was already powered. Then I end up connecting my USB cable, which is connected from my laptop, to my ESP32. What happens? Now the ESP32, your computer, your microcontroller, is getting power from 2 sources. It's getting power from battery, it's getting power from your laptop. Most of your laptops don't have inverse power protection, inverse current protection. If you get current reversal, you will burn something in your laptop. That's exactly what happened. It tripped a breaker in my laptop. My laptop fortunately had safety for that, so it basically tripped a fuse because there was back current. And in middle of competition, the code was just on my laptop. Nobody else had the code. My laptop went dead. I had to rush back home to get a 5-pin screwdriver because reasons, and we did it. So it was a whole panic. Why am I telling you this story? This is a collaborative team project. The point, we can turn the lights on. Turn the lights. The lights are there. Can we turn it on? Yeah. All right. The whole point of this thing is it's an engineering project for you. It's a collaborative project. You're all going to work in teams. More often than not, you're going to have multiple people programming. You need to share code. GitHub is a little bit too advanced for you. If any of you know GitHub, feel free to use it. But most of you are beginners. GitHub and version control and all of these methodologies are quite advanced, and not something, frankly, you need to get, you need to know. To get this successful, to be successful in this competition, you don't need to know this. But you need to be mindful that you share code, you have backups of your programming, you have backups. If you wire something, a really good practice, if you have wired something electronically and it works, take a picture of it. At any design stage, keep taking pictures of things that work. So at any point, some wires break loose or it breaks, something happens, you know what worked. Same goes for programming. Keep saving your code. Keep saving versions of your code so you have backup of it. Make sure you understand power and electronic and signal so you don't end up burning your laptop. If you do end up burning your laptop, to let somebody know. Most of your laptops have inverse current protection, so the battery shouldn't explode, but your computer will turn on. That's a safety feature. There are other resources here. Some of them are for you to learn. There are tutorials for you to learn how to use remote XY. There are tutorials for you to learn how to control the L298N motor driver using ESP32. There are some other tutorials that go over how to make an RC car using the exact motors and wheels that you have. And there are some other videos which go over the whole Arduino IDE setup and the rest of it. Give me one second. All right. So far, a lot of concepts thrown at you. 3 big things that need to take care of. This is a robotics project. Robotics is an amalgamation of electronics, programming, and mechanical. You have 3 big buckets. You have at least a 3 to 4-person team. You can either divide your task amongst people or figure out how the whole team is going to break down this project and work on chunks. Once you do, you have a lot of things to learn. If you already don't know, you have a lot of things to learn. And that is what a good project is. By the end of it, even if your robot does not work, you will know a lot of these concepts. And most of these concepts will come back to you in classes, in computer engineering classes, electrical engineering classes, mechanical, if you are MIEEE, it's going to come back to you in your electronics classes, controls classes, everywhere. All of these concepts. Analog, digital, how to control Wi-Fi, Bluetooth, network protocols, everything. It's a tough project. If you struggle, it's meant to be. You have to struggle. Nothing good ever came out of, I forgot the thing, nothing good ever came out without you struggling. That's okay. The point is, go through this slide again. You need to go through this slide again. Try to understand everything. Most of it is explained. If you notice, I didn't go with line by line because there are explanations which you can read on your own time. There are other resources links. There are other tutorials that we're gonna link. You're gonna get this work, this presentation with your rulebook. Like any good engineering challenge, you have a rulebook. You need to adhere to the rules. The rulebook mentions some components, modifications that you can do, modifications that you cannot. If you don't stick to the rulebook, at the day of competition, you're gonna get disqualified. All of this work will be for nothing. So it's your responsibility that you stick to the rule. The course for the race is not yet. Do you know about the race course? Like, is it out yet?
The exact course will be revealed on the competition day, but we will be sending out general information of what you might encounter.
Yeah.
But yeah, that's all going to be in the rulebook that we're posting today or tomorrow.
So the point I mentioned, the race course, is you're making this remote control fast RC car because for a competition. The competition is going to have a race course. It's going to have some sort of turn. Basically, this is an F1 competition. If you know any F1 circuit, they have sharp turns, straights. Sometimes you need to slow, sometimes you need to turn. There are a lot of dynamics. You need to make sure that your robot, this is not a programming challenge. This is also a huge mechanical challenge. Some people might not realize it now, but the design of your robot will make or break your robot. Even if your program works perfectly, if a robot cannot handle that speed, or if it cannot handle that turn, if the wheels don't have enough friction, it's not going to work. There are some things I would like to point. Simple hints these are hints that I would like you to give. You should have realized this on your own, but if you don't, these are the hints. First, the wheels don't have enough traction. You need to figure out a way for the wheels to stick to the ground better. Because if the ground is dusty like this, your wheels are just going to slip. You're not going to have enough speed because you don't have enough traction. Second thing, you are going to run out of battery. 6 volt, 1.5 amp batteries, the pack that is given to you is not enough power. So make sure your code is taking care of when the batteries are drained also. And on the day of competition, you're going to have multiple rounds, right? It's going to be...
Yeah, so we are going to be supplying fresh 4 batteries on the competition day, but it is a long day.
Yeah.
So it can drain.
It will drain. It will drain. The first comp, the motors, the high speed will be the highest speed. Throughout the day, your high speed will start decreasing. So your control needs to get more accurate or less accurate. You need to take all of these things into account. Another thing is the structure of the F1. People are going to drive together, right? They're going to be like rounds.
Yeah.
Just like an F1 race, there's going to be multiple cars. Things are going to bash into each other. You don't want to see your car doing a triple backflip on the F1 circuit and then end up like an actual F1 car, unusable. It will be fun. I am getting an actual slow-mo camera just for that. It's not going to happen, but I want to record some really high-quality slow-mo footage. All right. So you need to, this is a really good mechanical challenge because there's a lot of mechanical concepts that you might not have realized, but they are there. Electronic-wise, very simple. Already talked. You need to understand the gravity of all of the concepts, all of the signals and power electronics. Because if you make any mistakes, they are brutal mistakes. You're not going to be able to recover from the mistakes. But as far as wiring and electronics are concerned, you don't have that many components. It's very simple. All you need to take care of is your wiring is good. So in the middle of the competition, if somebody bumps into you, if your wire gets disconnected, your robot is not going to move. So you need to make sure design is redundant. Programming wise, you're going to get certain examples of code. You can copy paste the code and it will work, but it's not going to be the best. Why? Figure it out. This is actually the challenge. The code that is going to be provided to you lacks certain features. Once you use the code, once you have a car-ish and you use the code, you will realize it's not the best code. So now you need to work on the programming. So timeline-wise, what are the tasks? This is what you should do as a good engineer, as a good engineering team. Break down tasks timeline-wise. First, 4 weeks, right? Or 3?
Between 3 and 4 weeks.
Between 3 and 4 weeks. Enough time, but also not enough time. If you don't know stuff, first, get to know stuff. How do you know stuff? Hands-on practice. This is not a course. You don't read lecture slides. Try stuff out. Start with basics. There are some examples on the slides. Start with YouTube. Start learning stuff. By the end of this week or next week, you should have some sort of prototype there. Your motor should move at least. Your motor should move. Your Wi-Fi sketch is okay, but your motor should move. Everything. By the end of next week or the week after, you should have a car. You should have the electronics done, a car done. Because that way, a week before your actual competition, you should try the code that is provided to you by me. There's a code provided to you, but a week before, you need to try it on the actual robot for you to know, oh, what can be improved, what cannot be improved. What can be improved both on the software, but based on the software, what also can be improved on the hardware a week before. So you should have realistically a whole week of stuff working. This is something I should not tell you, but I'm going to tell you because this is real life. 60% of you are going to do this 2 days before the comp. This is a reality. It's going to happen because life happens. Not ideal. It is possible. I made this in 6 hours. You can definitely make this into 2 days if you have what it takes. If you are willing to pull all nighters and if you're willing to cut corners. What I mean by cut corners is your car will not be the best car, but it will work. It will move. If you want to slap a car together and make it work, you don't even need 6 hours. You need 2 hours. You need to slap 2 motors on a piece of cardboard, connect the wires, connect the ESP32, upload the code. That's it. At this point, I can make this robot in front of you in 20 minutes. So the reason I'm telling you this is realistically, it's not that difficult. The reason it's difficult is because you are a beginner and this is a complex project if you're not already familiar with all of the concepts. That's what makes it difficult. So it's a very simple project. At the same time, it's very difficult for you. Make sure team meetings and everything is up to you, how the team dynamics is up to you, but make sure you are breaking down tasks realistically and you are making sure to give yourself room for screw up because you're going to screw up a little. You're not going to have code on time. Make sure in your planning there is room for delays. You have more than 3 weeks, definitely more than 3 weeks. You need to start working on it as soon as possible. If you have any question at this point, show of hands. Any questions regarding timeline, technicality, anything, competition?
I have 3 quick things. So yeah, like I said before, fresh batteries will be provided on competition day. The full rule book, these slides and everything will be posted tonight or tomorrow. So then, well, the slides probably today, but the
They're gonna be together in the same email.
Yeah. And then the last thing, so I gave some of you a UN or a micro USB cable. For anyone who does not have that, since we ran out due to an issue this morning, we're ordering more, and we will have them Monday onwards. So basically, whenever you guys want, they're going to be at the IEEE lab. You can go on our website and see when the lab is actually open, and then you can just pull up and grab a cable from there, if any of you don't have one.
So what he said, now I have two things to add to it because I just remembered. One was one of the pitfalls we're talking about, a little hint. You need to, the reason I said that you need a week of actually testing the code and running your robot is you need to see the curve of the voltage drop. How long does it take for your robot to be useless? And based on that, you need to plan the day of completion, your strategies. I forgot to talk about strategies. On the day of comp, based on rule books, you need to have good strategy. Are you gonna be the robot that's gonna get other robots out of the ring? Like out of the track? Are you going to be the robot that's going to be the fastest? Are you going to be the robot that's going to be the most stable and most controllable? You don't care about speed, because some people, if they care about too much speed, they might go off the course, they're out of the race, or they might flip themselves, they're out of the race. So there are multiple strategies, multiple ways you need to focus, and that needs to start once you have something to play with, so that you realize, okay, I can do this, or I can do this, or I can do this. So 1 week is just bare minimum. Reasonably, by this weekend, you should have a robot. It's not that tough to build a robot. Hot glue 2 motors, a board, you're done. Second thing is, just so we mentioned, and just so I also mentioned in this slide, when do you know IEEE is open? You just go to IEEE Concordia, and you can see here on top.
Yes.
You can see here on top. The only light. Yeah.
Oh.
You can see here on top.
Yeah.
Is it open or closed? This is exactly the example I talked about. ESP32 wireless. There is a sensor on our lab, which is connected to an ESP32, which is connected to our router. The ESP32 is sending the signal to the router, it's connected to the website. If the door is open, we know the door is open. So there are many other projects beyond this competition that awaits you. The only thing you need to know is the only thing you need is curiosity and interest. All right, that was it. What? The reason I have sample code is I was going to paste the QR code here, but it's better if you all can get it via email, so that way you have the doc. That's it.
Yeah, so you're gonna get an email. I'm also gonna put in the Discord. And yeah, so you'll get all the rest of the information soon.
Again, just an FYI, a good engineer asks questions. I understand a lot of information was thrown at you, but you need to somehow piece together all the dots and come up with questions to better fill in the map. The concepts are a bunch of dots in your memory space. You have a lot of dots. Your job as an engineer, as a human, are to connect the dots, build the understanding and the intuition, two different things, understanding and intuition. Once you build those, you connect the dots of information. How do you connect those dots better? You ask questions. You can only ask questions if you try to understand stuff and then you figure out, oh, I didn't understand this, or how do I do this? The more questions you ask, the better you get. Another slight thing about ChatGPT, we are not a school course. You can use ChatGPT all you want. But the more ChatGPT you use, the less you understand. The more ChatGPT you use, at some point, if all of your code is ChatGPT and you don't understand anything, once something is going wrong, ChatGPT won't be able to help you. So my recommendation, use ChatGPT for concept building, to understand certain concepts. Let's say the programming concepts or the electronic concepts. If you don't understand, if you have doubt, use ChatGPT as your mentor to teach you the doubts. Never use, in your professional careers too, as a student or as an engineer, never use ChatGPT to write your own code. Slight note, I'm also a TA. I grade a lot of code and papers. Everybody, your markers, they all know if you write a report or a code using ChatGPT, if you're not careful about it, everybody knows what a ChatGPT code is like. We sometimes, ignore it because of reasons. We don't want everybody to fail the course. The point is, this competition, nobody cares. But you signed up for this competition for your own good because you wanted to become better engineers. So do yourself a favor and use ChatGPT wisely. That was it? Yeah.
We'll send you the team by today.
Yeah.
Thank you for coming.
Thank you, guys.
Oh, we are taking pictures. I don't give a shit.
Yeah.
I need pictures. I need to put it on.